So now we'll derive the Ehrenfest equation. So we will start with these two condition, S1 equals to S2 and V1 equals to V2. So first we'll take that the second order phase transition is occurring at temperature T and pressure P. Okay. So during this transition the temperature and pressure remain constant as well as the entropy, of course the Gibbs free energy and the volumes. First we take this S1 equals to S2. Okay, so at temperature T and P, suppose the specific entropy of phase 1 is S1 and the specific entropy of phase 2 is S2, so S1 equals to S2. Now if the same transition happens at a different temperature and pressure, T plus delta T and pressure P plus delta P, then its entropy, the values of entropy and entropies will be different. So but their values for phase 1 and phase 2 will be same. So S1 at temperature T plus delta T and pressure P plus delta P, the entropy is S1 plus ds1, and for phase 2 it is S2 plus ds2 and their values are equal. Okay. So now what we can do, S1 we can cancel S1 and S2 because they are equal. So we have ds1 equals to ds2. Now this entropy is a function of temperature and pressure. If we assume that entropy is a function of temperature and pressure, what we get? ds equals to del S del T constant P, this relation partial derivative. So from this relation what we can write, ds1 we can write it like this. Okay, del S1 del T constant P dt, and ds2 we can write it like this, del S2 del P, in this way, you know. So next what we'll do, we will replace this del S del P term using Maxwell's second relation. Okay. So del S del P constant T using Maxwell's second relation, we know it is minus del V del T constant P. So if we do so, what happens to this relation? What happens to this equation? It becomes like this. Del S1 del T constant P dt, first term remains same, second term becomes minus del V1 del T constant P dP equal to del S2 del T constant P dt, second term becomes minus del V2 del P constant T dP. Since here we have S1 S2, this V is replaced by V1 and V2. Next what we can do, this Cp1 by T, this ds1 dt can be replaced by Cp1 by T, and del V del T can be replaced by V1 alpha 1. Similarly, we replace the right hand side, the phase 2 term, by similar equations. So why we can replace it like this? Because we know Cp is equal to T del S del T constant P. So we had del S del T constant P, this type of term, which is equal to Cp by T. So for phase 1 we have del S1 del T as Cp1 divided by T, because we have already said that for phase 1 phase 2 there will be change of specific heat capacity at constant pressure, so we will use Cp1. Similarly we know alpha equals to 1 by V del T. So the next term we had was del V1 del T constant P or del V2 del T constant P, which is replaced by alpha 1 V1 or alpha 2 by V2. But then again V1 equals to V2, which let's say we take it to be V. So on both the sides V1 and V2 are replaced by simply V. So what we have here, Cp1 by T dt minus alpha 1, V1 is replaced by V. Here Cp2 by T, this minus alpha 2, V2 is replaced by V dP. Now we are taking these dP terms together, writing them together. Okay, and these dt terms together on the right hand side. So what we have, if we take V dP common, we have alpha 2 minus alpha 1, and here we are taking 1 by T common, we have this Cp2 minus Cp1. So finally what we have dP by dt equals to Cp2 minus Cp1 divided by dV alpha 2 minus alpha 1. So this is the first Ehrenfest equation.